The Global Positioning System, often called GPS, is now a feature of modern life, and it's found in many cars and cell phones. For instance, when you open up an online map on your phone, you might see a blue dot that seems to know where you are on the map. How does your phone know where you are? In this case, your phone is a GPS receiver, meaning it receives and interprets signals from GPS satellites in the sky, which are broadcasting both the location of the satellite and the time at which the signal was sent. If it has enough of these signals, your phone, which might not otherwise know where it is, nor what time it is, will be able to determine both its location and the time. We can get an idea of what kind of mathematical calculations are going on by thinking about a simplified example. And more details are going to be given in the Kalman reference in the guidebook. Suppose first that your phone knows the time, but doesn't know its position. Then, receiving one signal, your phone can look at the difference between the current time and the time at which the signal was sent, and, knowing the speed of light, can calculate how far the signal must have traveled. So your phone can infer that its location must be on some sphere of a particular radius centered around the location of this satellite. If your phone has two such signals, then your phone can infer it must be on the intersection of two spheres, each one centered at a GPS satellite. Two spheres generically intersect in, at most, a circle. Now, if you have one more signal, then that can be visualized geometrically as the intersection of one more sphere with this circle of intersection from the first two spheres. This can happen in at most 2 points. But if you know you are on the surface of the Earth, then you can usually rule one of those 2 points out. So we can see intuitively that if your phone knows the time and has signals from 3 satellites, then it could compute its location on the Earth's surface. Now, in reality, your phone GPS may not be keeping accurate time since it's usually not equipped with an atomic clock like the ones aboard the GPS satellites. So in practice, it is treated as an unknown. As we shall see, the extra degree of freedom requires a signal from one more satellite to narrow down both its location in space and time to one of 2 possibilities. And again, knowing you are on the surface of the Earth will usually resolve that ambiguity. So in general, 4 satellite signals are enough to resolve your location in both space and time. And the time information gained in this way can be used to constantly correct the clock on your GPS receiver. We've just given an intuitive explanation for the calculations we're about to do. Having our intuition guide our calculations is a very useful thing to do because this kind of sense-making will keep us from making inadvertent errors. So let us look at how signals from 4 satellites can be used to calculate your phone's position. We imagine our phone receives the following signals. The locations are given in coordinates whose origin is at the center of the Earth, and the units are measured in Earth radii. GPS satellites are in orbit at about 4.17 Earth radii, and you can use the Pythagorean theorem to check that these satellites are all located about 4.17 units away from the origin. The time that the signals were sent are all indicated in this table. The speed of light is about 47.05 Earth radii per second. So the total distance traveled is 47.05 times the difference in time between when the signal was sent and when it was received. So if t represents the current unknown time the signal was received, and by unknown I just mean your phone isn't actually necessarily accurately keeping time. And if xyz represents the unknown location of your phone, then the first satellite gives us the information in the following equation. The left side of the equation is the square of the distance between the phone and the satellite. The right side of the equation is the square of the distance the signal traveled between the time the signal was sent and the time it was received. Similarly, the other satellites give us 3 more equations. To find x, y, z, and t, we'll need to solve all these equations simultaneously. You'll notice these are not linear equations, since when you expand these expressions, these equations contain the terms x squared, y squared, z squared, and t squared. However, what I want you to notice is that x squared, y squared, z squared, and t squared all appear with exactly the same coefficients in each equation. This suggests you can cancel the terms if you subtract one equation from the others. So let's do that. If you expand the expressions and subtract the first equation from the other 3, the squared terms drop out, and you'll get the following 3 equations after all the algebra is done. This is a linear system of equations. How do we solve it? Well, in our last lecture, we saw that elementary row operations can be used to simplify a system of equations like this. In the ideal case we tried last time, we took an augmented matrix and used row operations that reduced the left side to the identity matrix. This corresponded to a situation where we had a unique solution. However, if we create the augmented matrix in this case, we have no chance of getting an identity matrix because the left side of the augmented matrix isn't even square. So in this lecture, we'll see how to handle this situation. In fact, we'll learn how to systematically solve any system of linear equations by using row operations to put the matrix in a special form called reduced row echelon form. Once we see how this works, we'll return to our GPS example and complete our analysis. Recall from last time that given an augmented matrix representing a system of equations, there are 3 elementary row operations that can be performed on it that do not change the solution set of that system of equations. You can swap 2 rows, you can multiply a row by a non-zero constant, and you can add a multiple of one row to another row, replacing that row. And the idea of Gaussian elimination is to use these operations to simplify a system. What could that possibly mean? Well, one thing it could mean is you'd like to eliminate as many variables from the equations as possible. This corresponds to increasing the number of zeros on the left side of the augmented matrix since they represent coefficients of variables. Notice that the third row operation is the one which will enable you to take a particular non-zero entry of an augmented matrix and make it 0. You'll do this by adding a multiple of another row to it. The important point here is to do this in such a way that you don't unintentionally make some entries non-zero that you already zeroed earlier. So we'll try to be systematic about it. The first thing we might try is to mimic our example from the last lecture, in which we used row operations to convert the left side of the augmented matrix to an identity matrix. This won't always be possible for many reasons. Here's one example where the left side of an augmented matrix is not square. And here is another augmented matrix where the left side is square, but no row operations will produce a 1 in the second column, since all entries in the second column are 0. So instead of an identity matrix, what we'll aim for first is something called row echelon form, which we'll sometimes abbreviate REF. Then we'll move to something called reduced row echelon form, which we'll abbreviate as RREF. The word echelon means step-like. It's best to first describe this form by an example. Suppose you have a system of equations, ax equals b, where A is a 3 by 5 matrix. Your goal is to use elementary row operations, which we'll abbreviate EROs, to reduce it to a form that has a step-like appearance. Here's what makes a form a row echelon form. On the left side of the augmented matrix, call the first non-zero entry in any row a leading entry. To be in row echelon form, the augmented matrix must satisfy two properties. The leading entry of any row must always be to the right of a leading entry in a previous row. And rows consisting only of zeros are at the bottom. Matrices satisfying these properties will have a step-like appearance, such that leading entries sit on the steps and all the entries below the steps are zero. Above the steps, apart from the leading entries, the other entries may or may not be zero. Now you may be able to see why row echelon form is always possible if you remember how we did row operations in the last lecture and tried to generalize it. Look at the first column. If there is any non-zero entry in that column, use a swap, if needed, to make the first entry of the column non-zero. That is the leading entry of the first row. Then add appropriate multiples of this row to other rows to zero out the rest of the entries underneath this leading entry. Now let's imagine we freeze the first row so we no longer can modify it. Then consider the second row, the current row. Now look at the second column. If all unfrozen entries are zero, move to the next column and repeat the process. If some unfrozen entries are non-zero, swap rows if needed to move a non-zero entry to the current row. This becomes a leading entry of the current row, and the current row can now be used on the unfrozen rows to zero out all the unfrozen entries of the second column. These operations will not disturb the zeros that already exist in the first column because the second row had a zero in the first column. Now freeze the current row and move on to the next row as current row. If you keep doing this in this fashion, you will produce a matrix in row echelon form. Row echelon form is nice because you can see some interesting things from it. It reveals some hidden structure of the original matrix A. For instance, if the row echelon form has a row of zeros, then one of the original rows of the matrix A must be a linear combination of the other rows. Also, the number of leading entries says something about the number of rows of A that are sufficient to span any linear combination of the rows of A. The number of leading entries is thus given a special name. We call it the rank of a matrix. We shall discuss the importance of the rank later on. And a matrix in row echelon form is easy to solve by back substitution, starting with the last non-zero row. That is one reason why people often stop Gaussian elimination at row echelon form, because you can often figure out what you need to from there. One thing that's not so nice about row echelon form is that it's not unique. If you tell two people to take a matrix and row reduce it to put it in row echelon form, they may come up with two different forms. Of course, the set of solutions will be the same because that's what row operations preserve, but the description of the set of solutions expressed by the row echelon form may be very different. This is where reduced row echelon form, which we are about to describe, is very nice, because it is unique for any given augmented matrix. If you give an augmented matrix to two different people and tell them to put it in RREF, they will give you back the same answers. Reduced row echelon form takes row echelon form and does a few more steps. Namely, it has two additional properties. Every leading entry is a 1, and a column with a leading entry has zeros in all other entries of that column. This is possible because you can just take row echelon form and multiply rows by non-zero constants to turn the leading entry into a 1. Then you can use a row with a leading 1 to zero out all the other entries in the column with that 1. Let's do an example. Consider the following system of equations. This has this augmented matrix. Looking at the first column, there is already a 1 in the first row. So we focus on changing the 5 in the bottom left corner to a 0. From row 2, we can subtract 5 times row 1. So 5 minus 5 times 1 is 0. 6 minus 5 times 2 is minus 4. 7 minus 5 times 3 is minus 8. And 8 minus 5 times 4 is minus 12. So this gives us this matrix. We recognize it as row echelon form because the leading entry in the second row, minus 4, is to the right of the leading entry in the first row. Next, we try to turn this into reduced row echelon form. We can change the minus 4 entry into a 1 by multiplying row 2 by a constant, in this case, minus 1/4. If we do this, we obtain this matrix. Finally, we need to zero the entry in row 1, column 2, because it is in the same column as row 2's leading entry. We can do this by subtracting twice the second row to the first row. This is now in reduced row echelon form because all leading entries are 1 and all other entries in columns with leading entries are 0. Note that we had many choices we could have made to row reduce this augmented matrix, but there is an important theorem that says no matter what choices of row operations we made, we must always get the same result for the reduced row echelon form. The theorem says for a given matrix, the reduced row echelon form is unique. Note that this theorem holds whether or not the matrix is augmented. To prove this fact is beyond the scope of this lecture, but we've included a reference in the guidebook. If you have an augmented matrix in RREF, there's an easy way to figure out the set of solutions. First of all, check if there are any inconsistencies. Remember, you can see if there are any by looking for a row of zeros on the left side of the augmented matrix equaling something non-zero on the right. If there are no inconsistencies, then we identify what are called free variables. Remember that for every column on the left side of an augmented matrix corresponds to a variable. Look at all the columns with leading ones in them. Call the associated variables leading variables. Then call all the other variables free variables. These variables are called free because they can be chosen freely to be any real number. If there are no free variables, then the leading variables will be completely determined, so the solution is unique. Otherwise, the basic idea is to use the RREF to express leading variables in terms of free variables. Since free variables are easy to express in terms of themselves, this will give us a way to express all the variables in terms of the free variables, which will lead to a parametric description of the solutions using free variables as parameters as long as solutions exist. To understand why, let's return to the earlier example in which we analyzed the RREF for this system. The reduced row echelon form was this. There's no row of zeros on the left, so there's no inconsistency. You can see the leading ones in the first and second column, and these are coefficients of x1 and x2. So x1 and x2 are the leading variables. The remaining variable x3 is thus the free variable. We can see the importance of the free variable if we examine the system of equations that comes from the augmented matrix, which must have the same solutions as the original system. The reduced row echelon form guarantees that leading variables appear in exactly one equation, but the free variable x3 can appear in many equations. Do you see that you can choose x3 to be any number you want? And once you do, x1 and x2 are now determined. As we mentioned earlier, this will help us to express all variables using the free variable x3 as a parameter. You see, the first equation allows us to solve for x1 in terms of x3. We see that x1 equals minus 2 plus x3. The second equation shows us x2 equals 3 minus 2x3. And what about x3? How do I express that in terms of x3? Although the RREF doesn't give us an equation that expresses x3 in terms of x3, That's okay, because I don't need one. It's obvious that x3 equals itself. So then I get a set of 3 equations expressing the set of solutions in terms of x3, the one free variable. This can be rewritten as a vector equation if I factor out the free variable. Since x3 can be chosen to be any real number, it can be thought of as a parameter. So you might recognize this vector expression as a parametric description of a line, because it is a point, -2, 3, 0, plus some parameter times a vector direction, 1, -2, 1. So the set of solutions to the original system is a line. Notice if x3 were 0, we'd see a solution to the original system is -2, 3, 0. And if x3 is 1, you'd get the solution -1, 1, 1. By plugging these into the original system, you can check that they are both solutions. Let's look at another example. Consider this system of equations. The augmented matrix looks like this. This matrix is already in row echelon form, as you can see by looking at the leading entries in each row. We can see that x1 and x3 are leading variables, and x2 and x4 are free. To make it reduced row echelon form, we should turn the 3 into a 0 by adding -3 times row 2 to row 1. Doing so, we obtain this matrix, which is in reduced row echelon form. And it corresponds to these equations. You see that the leading variables x1 and x3 appear in exactly one equation. Once you set the values of x2 and x4, which can be chosen freely, the leading variables are determined. We can solve for x1 and x3 in terms of x2 and x4 using these equations. And if we include the trivial expressions for the free variables, x2 equals x2, x4 equals x4, then we can express all variables in terms of free variables, like this. This can now be written in vector parametric form by factoring out the x2 and x4. Thus, the set of solutions to the original system of equations is just a linear combination of 2 vectors, -2, 1, 0, 0, and -1, 0, -1, 1. You may recognize this as a parametric description of a plane, in this case a plane passing through the origin, because it is the span of 2 vectors. Thus, the RREF was useful for expressing the set of solutions to a linear system. It can also be used to tell which matrices are related by row operations. Let's call 2 matrices row equivalent if there are a series of elementary row operations that take you from one matrix to the other. Then the following theorem is true. Matrices A and B are row equivalent if and only if A and B have the same reduced row echelon form. Let's prove this fact. First, if A and B are row equivalent, then there is a sequence of row operations taking you from A to B. But there is a series of row operations that take you from B to B's RREF. Putting these 2 sequences together give you a sequence from A to B's RREF. But this must then be A's RREF, since RREFs are unique. So A and B have the same RREF. Next, let's suppose A and B have the same RREF. Then there is a sequence of row operations taking you from A to the RREF. If we could find a sequence taking the RREF to B, we would be done, since there would be now a sequence of row operations going from A to B. But we know there are row operations taking B to the RREF, and since every row operation is reversible, we can reverse the sequence to obtain a sequence from the RREF to B as desired. So now we have a nice criterion to tell when 2 matrices are row equivalent. Now, we return to the GPS example from the start of the lecture. Recall that taking the signal from 4 satellites, we obtained a system of 4 nonlinear equations that had to be simultaneously solved. But since the nonlinear terms in each were the same, we could subtract one equation from the other 3 to obtain this system of 3 linear equations. We now know how to solve this, because its augmented form is this. And we can compute its RREF to get this. And this now corresponds to the following equations. Now, if t is chosen freely, we'll obtain a solution to the 3 linear equations. But to satisfy the original 4 nonlinear equations, we need to plug this into one of those equations. Suppose we plug these expressions into the equation from the first satellite. Then what you'll get is a quadratic expression in time, which can be solved using the quadratic formula. What you'll find is that either time equals 1.10 or time equals 0.934. The choice time equals 0.934 is seen to be nonsense, because then the signals would have had to arrive at the phone before they left any of the satellites. And if you recall, all the signals left the satellites after time t equals 1. We can also see that t equals 0.934 can't be right, because if you plug that value of time into the parametric equations we found, you will find the values of x, y, z whose vector length is not 1, so it cannot be on the surface of the Earth. The choice t equals 1.1 yields x, y, z equals 0.007, 0.594, and 0.801, whose vector length is 1.00 Earth radii. So this is on the surface of the Earth, and therefore we know these are the coordinates of the phone. So with just 4 satellites, we figured out how both the location of the phone, our GPS receiver, and also the time can be computed. There are currently at least 30 GPS satellites in orbit around the Earth, and it is for this reason that these satellites are placed in orbit in such a way that at any given time and at any point of the Earth's surface, there are always at least 4 satellites visible. Now, the data may have some noise. For instance, the signal may be slowed by the atmosphere, perhaps reflected by obstacles, so the location we compute may not be as precise as we might wish. However, if we had more satellite signals, and we often do, the accuracy can be improved using least squares estimate, which we can discuss in a later lecture.